Hello class, welcome to our video notes lesson on section 4.7 from our textbook. In this section we're going to learn some techniques and some formulas for integrating functions whose antiderivatives happen to be inverse trig functions. So to remember what types of functions have antiderivatives that are inverse trig functions, we should go back to and remember the derivatives, the regular derivatives of inverse trig functions. So if you can remember, this is from chapter 2, because the way we found these derivative formulas was by converting these inverse trig expressions into rectangular coordinates and then using product and quotient rules to come up with their derivatives. So we got these formulas. I won't go into how we derive them now, but we do need to remember what they look like. They have these x squareds in them, right? All of them have these x squareds. There are no trig functions, but there's these ratios. 1 over a square root or 1 over 1 plus x squared. For arc sine and arc cosine, we can see that the order of subtraction under the radical is 1 minus x squared. So we should remember that. And there's nothing outside the radical. It's just a radical 1 minus x squared. For arc secant and arc cosecant, we should remember that there is something outside of the square root. There's this absolute value of x there. And then the order of subtraction in these radicals is reversed from what it was in the arc sine and arc cosine derivatives. So one way to remember that it's x squared minus 1 versus 1 minus x squared, is that the x's are right next to each other. So in the secant, in the arc secant derivative, where you have your absolute value x out in front, the square root will immediately begin with an x squared so that these x's can be next to each other, and then that can remind you that the order of subtraction is reversed. For tangent, there is no square root, and it's adding 1 and x squared versus subtracting. So you could put this in any order, right? Order of addition doesn't matter. It can go either way. So when you see expressions that are either exactly this or in this format, then hopefully that would ring a bell. Wait a minute, that's the derivative of arc sine or arc tangent or arc secant, whatever it is, right? Another thing we need to keep in mind is that the derivatives of all the cos, I like to call them, right? These are the derivative of the cos. Cosine, cotangent, cosecant. They are exactly the same as the structure of arc sine, arc tan, and arc secant's derivative, except the only thing they differ by is a negative 1, right? This is negative 1 times the derivative of arc sine. This is negative 1 times the derivative of arc tangent and negative 1 times derivative of arc secant. So when you're going backward, since the derivatives only differ by a factor of negative 1, then you don't really need to know them when you're going backwards. So when we talk about integrals involving inverse trig functions, we really only have 3. You really just need to know these 3. The integral of 1 over the square root of 1 minus x squared dx would be arc sine, because this is the derivative of arc sine. Therefore, arc sine is the antiderivative of this. But what if it was minus? What if it was the derivative of arc cosine? You might think, well, don't you need to know that? No, because when we're integrating, we can just take that negative and bring it in front. So let me write this up here so you can see this is different. So if it was negative 1 over the square root of 1 minus x squared, we would take that factor of negative 1 and bring it in front and just think of this as the derivative of arc sine. And then we'd say, oh, that's just negative arc sine plus a constant. So you might be like, but that's different, right? That's not equal to arc cosine. And actually, it is equal to arc cosine. It turns out that, again, brief little review of inverse trig, but arc cosine is equal to negative arc sine plus pi over 2. Those two expressions have identical outputs. They're equal to each other. So actually, if I integrated, right, the derivative of arc cosine, if I integrated negative 1 over the square root of 1 minus x squared using this formula, which says, okay, pull the negative out and just think of that as the derivative of arc sine. And if I got, okay, then the answer to that is negative arc sine plus c, that actually is equal to arc cosine. So I don't need to use these Formulas when I'm integrating. And the same would be true of arc cotangent and arc cosecant. They're equivalent to these functions, or they differ from these functions by a factor of -1 and a constant. So therefore, it's okay to just use these three formulas. Now, you might see this version of each formula over here. This is the version the book gives you, and this is if u was some function of x, so maybe 3x or e to the x, or I don't know, just some other function of x, but in this format, and a would be some constant, so a number value, so some constant not equal to 0. Then if it falls into one of these three formats, where instead of 1 you have your constant squared, instead of x squared you have some function of x squared, you can use this idea of inverse trig functions also. So we're going to be looking at both using just the plain formula with x and then using the ones that have already sort of done a U substitution. Now on the AP exam, they don't really overstress integrals involving inverse trig functions that much, but when they do, they usually do have at least 1 or 2 questions, and usually it's involving an inverse sine or an inverse tangent. So I would say that these would be the 2 to really focus your energy on. We're still going to look at arc secant just so that you're not unfamiliar with it, but the stress is really going to go on these 2, the integrals that result in an arc sine or an arc tangent. So let's start here with example 1. So when you see something like this, you need to really have this in the back of your mind. You need to really be thinking, oh, that looks a lot like 1 over the square root of 1 minus x squared. It's almost exactly like it, which tells me that this must have something to do with arc sine, because the derivative of arc sine is in this format. So that's what I want you to be thinking about as you're about to solve this. So you can either use the formula, which I'll show you how to do in a second, or we can make it look like this using a U substitution. So that's method 1. So in method 1, I am going to first factor out the 4 under my radical sign. I'm keeping it in the radical just to kind of show you, because I'm trying to make this look like that. I'm trying to make it look like 1 minus something squared. So to make the 4 turn into a 1, I just sort of factor it out. But because the x squared didn't have a factor of 4, then when I factor out the 4, it becomes x squared over 4. So dx is still there. So then this becomes 1 over the square root of 4 separately times the square root of 1 minus x squared over 4. Of course, the square root of 4 is equal to 2. So this is kind of like 1 over 2, and I can pull it out of my integral. So now I'm here. So then it's like, I really would rather this be a u squared instead of x squared over 4, because then it would look exactly like this formula, only it would be in terms of u. So what we do to make that happen is we say, okay, I would rather it be u squared versus x squared over 4. If I could take out my x squared over 4 and replace it with u squared, then I get what I want. So then it's kind of like, well, then how would I do that? Well, then u squared would just have to equal x squared minus 4, right? They have to be the same in order to take this one out and replace it with u squared. So then I would have to figure out what u is then. So in order for that to happen, u would have to be x over 2, right? Square root of x squared is x, square root of 4 is 2. And in order for that to be the case, then du is 1/2 dx. Or I multiply 2 to the other side, so 2 du would equal dx. So now I'm ready to replace everything in this integral. The 1/2 is still out in front. And I have an integral of 1 over the square root of 1 minus u squared, because I said that u squared is x squared over 4, so I can take out the x squared over 4 and replace it with u squared. And then when I take out the dx, I have to replace it with what it equals, which is 2 du. So I have this constant of 2 that I bring out, and then I see that my constants are going to cancel. So then here I have what I wanted. I have basically the derivative of arc sine right here. Of course, now it's in terms of u instead of x, but that's okay. So this is arc sine u plus a constant, because that's the derivative of arc sine of u, if my input was u. But u was x squared, or sorry, u was x over 2. So I have to take that value for u and plug it back in so I get my final antiderivative in terms of x. So then I get arc sine of x over 2 plus a constant. So that's how we would do the antiderivative of something that looks like this using a U substitution. But the formula that was given in your textbook, this one right here, kind of has already worked out those type of U substitutions. Of course, they have things in terms of a squared and u squared. So you can use that as well. So let me just show you that. So here I have my integral of 1 over the square root of 4 minus x squared dx. You would just have to recognize, well, one, you'd have to memorize the formula, which is, well, I'll write it down in a second, but you'd have to know that this is a squared. A squared is 4, so that would make a 2. That would be u squared is x squared, so then u would be x. The formula says if you have something of that form, then you would get arc sine of u over a. That's what the formula says. So you kind of just have to sort of figure out what u is and figure out what a is. And so then this would equal arc sine of x over 2 plus a constant. So you get the same answer. See, this one's using the U substitution, this one's using the formula. And I'm sure some of you are thinking, what's the value of using a U substitution if this formula makes it so easy? The only reason I show you this method is because then you don't have to memorize another formula. You can kind of just keep the simple formula in mind. You would need to know these, right? You would need to know these, but you wouldn't have to know these variations of them. And you have a better understanding of how you get this answer. So I tend to advocate not memorizing too many formulas, but just deriving answers. But some of you are really good at memorizing formulas, so I still wanted to show you that you can just do that. You can just memorize the formula and get the same answer that way too. Now in example 2, the function that we're taking the antiderivative of looks a lot like the derivative of arc tangent. Now, of course, the addition's been switched around, so maybe it's not as obvious, but it's basically 1 over x squared plus some constant. So I would hope that we would be thinking about, that's the derivative of arc tangent, so I know that my antiderivative is going to involve that function. But except I have this like pesky 2 right here. So if I'm going to do this using a U substitution without a formula, I'm going to factor out that 2. But of course the x squared term didn't have a 2, so that means it has to now be dividing by 2. Right? If I were to distribute the 2 back in, these 2's would cancel and I'd have x squared plus 2. So I'm factoring the 2 out, and then I'm going to think of that as 1/2 times 1 over x squared over 2 plus 1 and pull it out. So I pull the 1/2 out. So now I just have this. Getting closer to looking like that. So I'm going to think, well, I would really rather that be a u squared. If that's a u squared, then pretty much I have this, right? Because I could think of it this way. The derivative of arc tan of u, derivative with respect to u of arc tan u, would be 1 over u squared plus 1. So then the antiderivative of this would just be that. So that's what I want. I want just a u squared there. But it's an x squared over 2. So I want u squared to be the same as x squared over 2. And then I can just swap out x squared over 2 for u squared. So then the question is, well, what would u have to be for u squared to equal x squared over 2? It would have to be the square root. So it would have to be x over the square root of 2. Or 1 over the square root of 2 times x. So then the derivative of that is just 1 over the square root of u dx. So then if I'm getting my dx alone, I bring my square root of 2 to the other side, I can see that dx can be replaced with the square root of 2 times du. So then I've got my 1/2 in front. I am now going to swap out my x squared over 2 for u squared. So I have 1 over u squared plus 1, which is what I wanted. And now I can swap out my dx for rad 2 times du. So I have another constant here that I can just sort of pull out. So then this would equal rad 2 over 2 on the outside, and then 1 over u squared plus 1 du on the inside. That's just the derivative of arctan u, right? If I'm doing this with respect to u, is kind of like my x. So then the antiderivative would just be rad 2 over 2 times arctan of u plus a constant. But u, we had figured out earlier, was x divided by rad 2. So then this would be rad 2 over 2 times arctangent of x divided by rad 2 plus a constant. So there's my answer using just a regular U substitution, not any sort of new formula. But I could get that same answer using the formula. So here's my original integral. Here's what the formula looks like. It goes a squared plus u squared. Now remember, u is the function of x and a is the constant. So the order can be switched, which it was here. So here my a squared is 2 and my u squared is x squared. So u is just x. I can just replace x with u and a with the square root of 2. Now the formula says that this will then equal 1 over a times arctan of u over a plus c. A was the square root of 2, so it's 1 over the square root of 2, and then u was x, and the a was the square root of 2, plus c. This answer is the same thing we got here. Of course, here using this method, our fraction was rationalized. So it's okay, either way, the square root of 2 over 2 is equal to 1 over the square root of 2. So however you write it doesn't matter. These answers are equivalent. So this method, of course, was using the U substitution. This one was using the formula, and you are welcome to use either one. So why don't you try these two? So for part A, this should be your answer here. 1 over 4 times arctangent of x over 4 plus a constant. I solved mine using a U substitution by factoring out the 16 in the denominator, so then pulling out a 1 over 16 in front of my integral. That left me with this x squared over 16 that I wanted to replace with u squared. So I had to say, okay, well then u squared needs to equal that. And if u squared equals x squared over 16, then u would equal x over 4, because I'd have to square root both. If u equals x over 4, then du is 1/4 dx, which makes dx equal to 4 times du. So when I go to replace dx and x squared over 16, I replace the dx with 4 du, because that's what it equals. I replace x squared over 16 with u squared. And then the 4 can be brought out of the integral, reducing with 16 to make 1 over 4. And then this right here is just the derivative of arctangent. So the antiderivative of that would be arctangent of u, right? This is with respect to u. But u was equal to x over 4, so I just resubstitute that back at the end. You could also use the formula here where a is 4 and u is x. For B, you should end up with 1/5 arcsecant of x over 5. Oh, I should put that in absolute value. Put your x in absolute value to ensure that the values inside arcsecant stay positive. And then I got this by using a U substitution and factoring out the 25 that was under the square root. But I could also use the formula where a squared is 25, which makes a 5, and u squared is x squared, which makes u x, although we have to put that in absolute value in here. This should be absolute value right there. And then when I use the formula, it's 1 over a arcsecant absolute value of u over 5, or over a, excuse me, plus a constant. So a was 5 and u was x, and so I just plugged everything in. So you could also just use the formula for that one. So in example 3, it's like a little bit more challenging version of one of these type of problems, but I still would hope that when you see this, like constant times something with x squared, that it would make you think of this. Granted, it's a like more complicated version, but I would want it to make you think of this, and then you'd be thinking, that's the derivative of arctangent. That's kind of how I want you to look at this. So then when I'm doing the antiderivative, it's probably going to involve an arctangent of some kind. And then think, how can I make this look like that? So the first thing we could do, if we're using a U substitution versus the formula, the first thing we could do would be to factor out a 2 in my denominator, because I want to make a 1. I want my constant to be a 1. So factoring out a 2 could make that happen. I just have to realize, okay, well, there was no factor of 2 here, so then I just have to divide by it. That way, if I were to distribute it back in, the 2's would cancel, and I would have 9x squared. But since I factored it out, now I have 9 over 2x squared. And then think of that as 1/2, right? 1/2 times dx over all this. So I can take that 1/2 and pull it out of the integral. And I have 1 plus 9x squared over 2. And then I think, okay, I would rather that be u squared, because then it will look just like that. Of course, except it with u, but that's okay. We could just think of those as u. Okay, so for me to be able to replace 9x squared over 2 with u squared, I just make them equal to each other. If they're equal to each other, then I can just swap this one out for u squared. But then the question is, well, then what's u, right? We've got to know what u is at the end when I'm doing arctan u. Well, it would just be the square root of all this, so 3x over the square root of 2. So then if that's u, then du would just be this constant being multiplied to x, right? 3 over square root 2 dx. But if I want to figure out what dx equals so I can replace it, I need to multiply by the reciprocal. So I get rad 2 over 3 du is equal to dx, right? Multiply by the reciprocal to cancel it out. So that's what I'm going to replace this dx with. I'll replace it with rad 2 over 3 du. Okay, so now I've got my 1/2 that I pulled out earlier. I'm going to think of this as 1 over all that times dx. So 1 over 1 plus u squared times dx, which is equal to rad 2 du over 3. This is just a constant that I can pull out as well. So then I would have rad 2 over 6 outside of my integral, and then 1 over 1 plus u squared inside my integral. And that's just the derivative of arctangent with respect to u anyways, right? If I took derivative of arctan with respect to u, it would be 1 over 1 plus u squared. So when I'm doing the antiderivative of 1 over 1 plus u squared with respect to u, that's just arctangent of u times my constant. So constant times arctan of u plus c. But u, we had determined earlier, was 3x over the square root of 2. So then my final answer would be rad 2 over 6 times arctangent of 3x over rad 2 plus my constant. So there is my answer, just using a U substitution and remembering this derivative fact. We could find this using the formula though. It still requires a mini U substitution. So let me kind of show you how that works. So the formula says, okay, if you have du over a squared plus u squared, that's equal to 1 over a arctan of u over a. So I would have to realize that if I'm comparing it to this integral, that a squared is 2. So then a is the square root of 2. And u squared would have to be 9x squared, which would make u equal to 3x. So if I'm using the formula in this case, because this was not just plain x squared, I do still need a u substitution. So if u is equal to 3x, then du would be 3 times dx. So when I go to replace my dx, I need to remember that, let me divide by 3 here, that it's equal to du over 3. So I need to rewrite this integral. So dx needs to be replaced with, I'm going to think of this as 1 over 2 plus 9x squared times dx. So I'm going to think of that as times du over 3. And then I'm replacing that with, I guess, 2 plus u squared. So I'll pull my 1/3 out. So this is like my a squared plus u squared. So then I can do 1/3 times the formula. The formula says 1 over a. But see, this is not taking into account anything you might have to multiply outside the integral, right? I had a 1/3 outside the integral because of my dx equaling du over 3 right here. So now I multiply that to the formula, 1 over a, which is 1 over the square root of 2, times arctan of u over a. So u was 3x and a was rad 2, and then plus c. So then you can see here I ended up with 1 over 3 rad 2 arctan of 3x over rad 2 plus c. So I still get the same answer. Again, because of rationalizing the denominator, right, these numbers are the same. Rad 2 over 6 is equal to 1 over 3 rad 2. Those are the same number. For some reason, when you do the U substitution method, it already rationalizes the denominator. And when you do this, the formula, it doesn't. But it's okay. You don't have to rationalize the denominator. But you can see, you get the same answer. It still required a mini U substitution, though. So using the formula doesn't mean you won't ever have to do a U substitution. You just kind of have to be careful and look what U is, basically. So I want you to try one that's a little trickier, but I'm going to give you some hints. So you might see this x out here and think, oh, arcsecant, right? Because the derivative of that has the x in front of the square root. But then it also has the x right next to it. If the x's are not right next to each other, it's not arcsecant. So this is not going to be a derivative of arcsecant. So then arcsecant is not going to be part of our answer. That x on the outside will have something to do with the fact that u, so u in this case is going to be ln of x. So that's my hint. Let that equal u and see what kind of integral you end up with after converting over completely to u, and then see what inverse trig function might be at work here. Okay, so your final answer should end up using arcsine. It should be arcsine of the natural log of x plus a constant. Now, how did we end up with arcsine? Well, what happened was, because u was equal to ln of x, the derivative of that equals 1 over x. So it's kind of like right here, right? This is 1 over x dx. So this combined with that is equal to du. So when we replace dx with du, those x's go away, right? Of course, the way I do it is I multiply the x over here. So dx was equal to x du. So when I took out the dx, or when I replaced it with x du, these x's just remove themselves, and so it's gone. So now I'm integrating just 1 over the square root of 1 minus u squared du. When the order of subtraction is 1 minus the variable squared under the radical, that's the derivative of arcsine. Of course, this was with respect to u. U is our variable. So it was arcsine of u plus a constant. But what was u? U is equal to the natural log of x. So I just replaced that back in there, and there's my final answer. You're probably looking at this thinking back to pre-calc days when you probably never thought we were going to take the two hardest functions and put one inside of the other as the answer to a question. Forget about all the work in between. That's what the answer was. So yeah, welcome to calculus. Let's move on. So now we come to example 4, where we address this situation of having to recognize when to use inverse trig and when not. So you might come to something in with this integral in part A and recognize, okay, that's 1 over the square root of 1 minus x squared, and maybe that would ring a bell, that's the derivative of arcsine. I hope that would ring a bell. And then you say, oh, well then the antiderivative of this is just arcsine. Plus c, obviously. Because this is just the integral of the derivative of arcsine, therefore the antiderivative is arcsine. It's all about knowing your derivative formulas and being able to recognize them. But then you might begin to think the same thing if you come to something like this in part B, you still see that 1 over the square root of 1 minus x squared. So you might be thinking, okay, this might have an arc sign in it. But because of this x in the numerator, this is actually just a regular u sub, where we our I kind of goes to the inside of the function. We could let u equal 1 minus x squared. Our du would then be negative 2x dx, so I can see the x dx part is right here. If I isolate dx to get du over negative 2x, I can see that when I substitute that in place for dx, like when I move this out and replace it with du over negative 2x, my x's will cancel. And I'll get this in my integral. So I'd have the x right here, that was in my numerator, divided by the square root of what I'm now going to call u, right? U is equivalent to 1 minus x squared. Multiply that by what I'm now going to call du over negative 2x, because that's what dx equals. So I can replace it with that. When I do, I see that my x's cancel. So by just using a regular u substitution, I was able to convert this entire integral to be in terms of just u. Now I have 1 over the square root of u. I can think of this du divided by negative 2 as negative 1/2, right, times du. So I can pull the negative 1/2 out of the integral. So it's just the integral of 1 over the square root of u du. I can just think of that as the integral of u to the negative 1/2 and use a simple power rule for integrals. I won't finish it now because the point was just this. It can be solved using a regular u substitution and a regular antiderivative, just using a power rule. It did not require inverse trig because of this x in the numerator. Okay, so then you might come to something that looks like this one in part C, where now the x is in the denominator. So maybe you would try a u sub. You would start by letting u equal the inside part. You would get du equals negative 2x dx, right? It's kind of following the same steps as the previous one. And maybe you would get here. And then you would realize, wait a minute, when I go to replace everything and try to get it in terms of u, my x's wouldn't cancel because I'd have 2 of them in the denominator, this one and this one. They don't cancel. So this integral would not be able to be solved with a basic u sub. Couldn't do it that way. So then you might be thinking, that looks a little bit like the derivative of arc secant. The derivative of arc secant has that x in the denominator and a square root of x squared minus 1, and this is close enough, maybe you would think. Actually, no, right? These are not equal to each other. In fact, they differ by a negative. So maybe you think, okay, I could think of that as x times the square root. Maybe I could factor out a negative 1. If I factor out a negative 1, that turns 1 minus x squared into x squared minus 1. Maybe I could somehow make a secant out of that. But what are we working with here? That's an imaginary number. I would then be multiplying by an imaginary number, and I can't integrate imaginary numbers, at least not using basic integration techniques. So this is not actually the derivative of arc secant. It differs by a negative under a radical. So I can't use inverse trig here. In fact, this one we are unable to integrate using basic integration techniques. So we need to be able to recognize, because it looks so similar to A and B, but it was actually different enough to the point where we weren't even able to take the antiderivative of it. And A and B look very similar, but A required inverse trig and B did not. So it's all about our ability to recognize when we need inverse trig, when we don't, and when we can't even use inverse trig. So now we come to example 5, which is our first challenge problem, because again, this is quite difficult to recognize. And because it has an x to the first, we might think, okay, let's use a regular u substitution, right? We would let u equal the thing under the radical because it's, quote, inside, right, the function, how we did this before. But when we would go to find du, the 4 would go away. Derivative of a constant is 0. I would get negative 2x dx, right, a single term. Divide by the negative 2x to get dx by itself. And so I would run into a problem right here where I go to try to replace, right, to get everything in terms of u. I replace dx with du over negative 2x. I would notice that because this has the plus 2, I can't cancel it with this x. These x's actually can't cancel. So then I end up with like 2 factors of x in my integral. So not only have I not gotten rid of x, I've actually doubled it. So I've got u and x. So actually this isn't going to work, right? A basic u substitution is not going to work. So then what should we do? That plus 2 was the thing causing the problem. So I wonder if we could break this up into 2 fractions over that plus sign, right? So we'd have x divided by the square root of 4 minus x squared plus 2 divided by the square root of 4 minus x squared. These expressions are equivalent because x and 2 both had a common denominator. That's why they were being added together in the numerator. So I could break them up over that common denominator and add them as 2 separate fractions, which then allows me to break up my integral and integrate these as 2 separate integrals. One of them could be solved with a basic u sub. That's this one. The other one could be solved using arc sine. Of course, both of those are going to require some work. So maybe I'll actually come back to this over here. Let me erase this part. So I can use this work over here on just this first integral because now my x will cancel because now I have a single x. So I'm going to replace my 4 minus x squared with u because I'm saying that those are equal. So I get square root of u. I'm going to replace my dx with du over negative 2x because I'm saying those are equal. And now my x's will cancel out, and this integral can be solved with this u substitution. I'll think of this as negative 1/2 times du, and I'll pull that out. So then I get negative 1 over 2 times the integral of 1 over the square root of u du. I'll solve that in a second. Meanwhile, with this integral, I can take this constant of 2 and pull it out. So now I'm just looking at 1 over the square root of 4 minus x squared dx. I think for the sake of time, I'm going to just use the formula method on this one. So what does that formula say? It says that if you have an integral of 1 over the square root of a squared minus u squared, that is equal to arc sine of u over a plus c. You can see here my a squared is 4. That would make my a 2. My u squared is just x squared. So actually u is just x. So du is equal to dx. So I can just go ahead and use the formula on this one. It actually won't really require a u substitution since u is x. They're the same thing. So I can just say that this integral would be, so I have the 2 times arc sine of u over a, but u is x, and a is 2, and then of course plus c. So this integral is done. Over here I just have to do a simple power rule. So I have the integral of u to the negative 1/2. So the antiderivative of that, I add 1 to the power and divide by that. So I'd have negative 1/2 times u to the 1/2 divided by 1/2 plus a constant, and then of course these 1/2s will cancel, but I still have a negative 1. Now this constant and that constant can combine, right? We always combine constants. That's why we always just sort of add 1 at the end. The 1 we add at the end sort of represents a combined constant. So now I have, this is equal to negative u to the 1/2 plus 2 arc sine of x over 2 plus my 1 combined constant, right? So this c that I add at the end is just a combination of all other c's, all other constants that came before. That's my combined constant. And then all I have to do now is just resubstitute back in what this value of u equaled. So that came from this work over here where u was equal to 4 minus x squared. So I sub that back in here. So I have negative square root of 4 minus x squared plus 2 times arc sine of x over 2 plus my combined constant. And that is my antiderivative of this original function, the one we see in this integral right here. And again, I don't have the time to show you, but you would see that if you took the derivative of this, right, this would require a chain rule, so with this, and there would be some simplifying that we could do. Once we took that derivative and simplified it, it would in fact equal this function here. Now this last challenge problem, we are going to do this together in class, so don't miss it, and I'll see you there.